Today we are going to start our chapter on energy, and we're skipping all the way to chapter 12. You did the vocabulary the other day. You've watched a Bill Nye on energy. So now we're going to jump in. And this is similar to our social studies and the way we're doing it as far as getting to the videos. All the videos are embedded in this way, which is what this presentation is called. And you will come back and watch the videos because I'll have the link for you in your instructions for today. All right, so to navigate again, you go down to the lines with the 2 dots. If you go to the arrows, you're going to have to go through all slides. If you go to the line with the dots, it'll take you kind of like to your table of contents. You can see where we were. Here are the songs, and then here are the lessons that go with chapter 12. And we're going to begin with lesson 1. So the songs are similar to social studies as well. You can go back and listen to those while you're working. Actually, I encourage you to do so because if you're a musical learner, this will help you learn the material. So 12.1, what is energy? We have 3 objectives in today's lesson that you should be able to do by the end of the lesson. Explain the relationship between energy and work. Compare kinetic energy and potential energy. Describe the different forms of energy. So this is one of the videos you will come back and watch, a study jam. So energy is the ability to do work. Okay, well, what is work? Work is the transfer of energy. So work is done when a force causes an object to move in a direction of the force. So it's like you pushing something. It takes energy to do that. So energy is the ability to do work. Work is simply you transferring that energy. Energy and work are expressed in units of joules. Notice the spelling. It's not like a diamond ring. Joules, joules, and it's represented with a capital J. So here is an example of energy and work. The tennis player does work, transfers her energy to the racket, and then with this energy, the racket can do work on the ball. So energy is being transferred from the person to the racket to the ball. This will be another video that you will come back and watch. And then you have a brain pop that you're going to watch as well on kinetic energy. So the energy of motion, all moving things have kinetic energy. So if it is moving, it has kinetic energy. And there are 2 things that kinetic energy depend on: an object's mass and an object's speed. So if you know an object's mass, which is represented by lowercase m, and its speed, which this V, that looks kind of funny. There's another word for speed. It's called velocity. So that's why speed is represented with a V. So if you know the mass and the speed, you can calculate the object's kinetic energy using this equation. And there should be a bar here, a division bar. Kinetic energy is equal to mass times the speed squared divided by 2. Okay, so we said that kinetic energy is anything that is moving. If it is moving, it has kinetic energy. Now we're going to shift our focus to potential energy, and you have a brain pop as well to watch on potential energy. So if moving is kinetic, potential is position. So think of P and P. So the energy an object has, because of its position, where it is potential energy. And there are different types of potential energy. We have elastic potential energy, gravitational potential energy, and we're going to break each one of those down into a little bit more common knowledge here. So with elastic potential energy, this type of energy can be stored in objects like bowstrings, springs, and rubber bands. So it's the energy put into stretching like a rubber band that becomes the elastic potential energy. Okay, so moving kinetic based on its position potential. If stretching is involved, we have elastic potential. So in other words, that rubber band isn't going to get up and do any work by itself. You have to pull the rubber band back. So you have to transfer your energy to it. The next is gravitational potential energy. This is the amount of the amount of energy that an object has depending on its weight and its height. So gravitational potential energy equals weight times height. And just think about gravity. If you're going to drop something, it's going to fall down. That's because we live on Earth, and Earth has gravity, so everything goes down. So gravitational potential energy is equal to the amount of work done on an object to lift it to a certain height. Okay, so now you're scratching your head and going, height above what? When you watch the brain pop, this will make more sense. So when you find out an object's gravitational potential energy, the ground that you measure the object's height from depends on where it is. Is it from a tabletop that's 4 feet tall, or is it from the top of the refrigerator that's 10 feet tall? And then the height you use in calculating gravitational potential energy is the measure of how far the object has to fall. And then I have a funny video that you're going to come back and watch. And these are called Eureka videos. So several videos in today's lesson to help you understand this material. Okay, so we've done kinetic, we've done potential. There are 2 types of potential, elastic and gravitational. So now we're going to talk about mechanical energy. Mechanical energy is simply when you add potential energy plus kinetic energy. So you're adding the motion and the position. So it's the total energy of the motion, which is kinetic energy, and the position of the object, which is potential energy. Both kinetic energy and potential energy are kinds of mechanical energy. They remain the same unless it transfers some of the energy to another object. So even if the mechanical energy of an object stays the same, the potential energy or the kinetic energy can either increase or decrease. So in other words, when you add them together, you're always going to get the same thing. You may have more kinetic energy this time than you do potential energy, or next time you may have more potential than you do kinetic. But when you add them together, you're going to get the same amount. Thermal energy. Take your hands and rub them together really fast. Keep doing that for a little while, and you're going to realize that your hands heat up. So all of the kinetic energy due to the random motion of particles that make up an object is this thermal energy. All matter, this is very important, all matter is made up of particles that are always in random motion. So all matter has thermal energy. So if you're sitting at a table, that table is matter. It's made up of these tiny particles. And you're going, well, it's not moving. The table's not. No, the table's not going to get up and move off. But if we were to put a microscope over it and magnify it a lot, we would be able to see those tiny particles moving around. So all matter has motion. All matter has thermal energy because the particles are moving. So thermal energy increases as temperature increases, and it also increases as the number of particles increase. So that's easy to remember. It increases both times. So here we have thermal energy in water. So the particles in an ice cube vibrate in fixed positions. In other words, they don't have a lot of kinetic energy. It's kind of like when you're standing there and you're shivering when you're cold. They're still moving, but they're vibrating. They're not bouncing all around. The particles of water in a lake, which is a liquid, can move more freely. They slide past each other. And then in steam, wow, look at those particles. They are getting after it. They are colliding into each other and saying, don't touch me, don't touch me, don't touch me. It's kind of like when you get hot. Don't touch me, I'm too hot. Okay, there's another brain pop that you're going to watch that's going to combine all of this into forms of energy. Chemical energy, that's the energy of a chemical compound that changes its atoms. In other words, it's rearranged. It is a form of potential energy because it depends on the position and the arrangement of the atoms in a compound. So the energy that you put in your body by eating food is chemical energy. A change takes place. And this is kind of gross, but this is how you can remember it. That food doesn't look the same way when it comes out as what it did when it went in, does it? So your body has made some chemical changes to it in order for it to be able to use it. Electrical energy. Think of E. It is the energy of moving electrons. Electricity, electrons. So it can be thought of as potential energy that's used when you plug in an electrical appliance. That's how that thing works. Sound energy. You're going to have a video to watch. It's caused by an object's vibrations. And the object's vibrations transmit kinetic energy to the air particles, which also vibrate and transmit sound energy. So it moves through waves. And light energy is produced by the vibrations of electrically charged particles. Last but not least, we have nuclear energy. And there's a brain pop for you to watch on that, and I have a funny video as well. Nuclear energy comes from changes in the nucleus of an atom. It can be produced when nuclei are joined in fusion. Clasp your hands together. So a fusion reaction, or it can be when the nucleus is split apart in a fission reaction. So fusion joined together, fission split apart. Think about carbon dioxide when you pour a Coke or a Dr. Pepper and the fizz coming off. So fusion joined together, fission separated. There's a funny video. Actually, this is not a funny video. It is funny, but it's about sound energy. And now this is the really funny video. You'll get a kick out of it. And then eventually there will be another Bill Nye that you'll watch. And next time we will pick up with lesson 12.2, which will be energy conversions.